quick introduction. So my name is Eitan Vesely, coming from Israel. I was the founder and CEO of Senso, which I will dive into details later on today. Presenso was acquired by SKF 6 months ago, and now I'm acting as the AI offering manager of SKF. Few points today. We will have a webinar around industrial analytics and also from the SKF point of view. Feel free to ask questions. You can use the chat, the Q&A option to ask questions both anonymously if you prefer. In the case that you are interested in more details to learn more about the solutions that SKF has and Enlight AI in particular, feel free to contact your local SKF representative and they will channel it internally to the right people. So let's begin. And again, feel free to ask any question on the Q&A. I will reserve the last 10 minutes for that. Perfect. I hear some echo, so whoever is not speaking, Tuve, I think it's you can. If you can mute, it will be helpful. So, when we look at the industrial market, we are all familiar with the term Industry 4.0. Basically, the industrial sector is being disrupted by technology in all sorts of ways. And of course, technologies, when they come and they're new, in many cases also constitute or dictates new business models. So the traditional, I would say, OEM business model is capital expenditure, transactional deals in which they sell their equipment or components. And then for the customer, of course, it's the lifetime parts and maintenance cost, and also the cost of downtime. And again, traditionally, and in most cases, this would be the general TCO model, or the total cost of ownership. And if we now dive a bit deeper into the downtime part of it, so as you can imagine, a lot of work is being done to reduce and minimize the downtime as much as possible. And therefore, in the last few even decades, the trend was, or the market is moving from the reactive maintenance, where the asset would fail, the cost to repair would be the highest already. Then moving to more preventive maintenance every 6 months, 3 months, 9 months, whatever, to proactively go and maintain the parts, the machine, whether needed or not needed. Then the traditional predictive maintenance, mostly vibration monitoring, thermal imaging, oil residue analysis, all these walkarounds to collect samples of data or oils from the plants. And today, again, it's part of the Industry 4.0 transition. Machine learning based predictive maintenance is also joining that mix. And of course, the goal is to catch the failures as early as possible before they affect the production. And when we look at the market, we find various different methods for predictive maintenance. The first, and again, the more traditional type, would be the acoustic and vibration sensors. Most of it vibration sensors, acoustic is also now emerging, but the point is these are hardware-based solutions. They all require the installation of new instrumentation in the plant. From the other side, we have 3 different types of software-based solutions. where the first one would be then a well-known digital twins, or in some cases expert analysis. So in that case, a model of the machine, a model of the asset, a digital model of it. When we speak of the digital twin, these are physically based models or simulations of the actual assets, which means that in order to generate such a model, it requires or even relies on the expert's knowledge. And therefore, this is usually the OEM solution. Then we saw the market moving a bit further into ML or machine learning based solutions. In that case, manual data-driven modeling. So as opposed to a physical model here, which is built from a bunch of physical equations, in that case, we're talking about data-driven models, machine learning models, statistical models, which are built from looking at the data without knowing or without incorporating the physical equations into it. And in that case, we saw, or we have today in the market, various different types of model generation environments. And the expectation is that the customers will have their own team of data scientists, which is capable to work with these environments, take the machine data or process data, and build their models by themselves. And here I would say that the main gap is that these two methods are built or based on manual work done by data scientists or engineers. Eventually, if the model is built manually, whether physical or statistical, it means that someone will need to continuously maintain the model, adapt it, verify that it's right. And for that sense, the labor-intensive work of building and maintaining the model, this is now we also see today in the market the transition towards, or should I say, the development of automated machine learning based solutions. As many other things in our lives, automation makes things more easy, and in that case, most of the work of the human data scientist was automated, and therefore there is a very limited dependency on humans in the loop here. And we will dive deeper into AutoML in a few more slides. But just to try and summarize, this is our view of the market and the segmentation to the various different types of solutions that we found out there. Each one of them, of course, has its own advantages and challenges. So when it comes to accuracy, most cases, the expert knowledge-based analysis would be the most accurate. When it comes to identifying the root cause, in that sense, vibration sensors usually provide the best or the better insights towards the failure mode or the root cause. When it comes to scalability, no question that AutoML is by far has the lead here, identifying or providing a time to failure estimation. Here too, our view is that vibration sensors analysis does provide the most prolonged time to failure. And of course, very important for in today's economy especially is the cost, and in that case, given the low computational the prices of computational resources today, given the cloud, AutoML is considered to be the most cost effective. So as you can see, they all have their advantages and challenges. Looking at vibration sensors, digital twins, and manual data modeling, they're all here for decades, I would say, on and on. And when it comes to automated machine learning or AutoML, in that case, we're talking about rather new and emerging technology. So at this point, let's spend a few more minutes on AutoML and what does it mean. And the first question to be answered is, why is even AutoML an option? Why is it considered one of the four methods, and why do we see it emerging in the market? And there are a few contributing factors to that. First of all, when it comes to AutoML, in most of the cases, it's a single solution for multiple types of machines. So it's not a dedicated solution for a specific model of make, a specific OEM. And as you can imagine, industrial plants, they do not wish to work with 5, 10 different monitoring systems for each one of their equipment or OEMs. And here, AutoML comes very handy as it serves multiple types of machines with the same exact software solutions, whether it's the core equipment of the plant or the auxiliary equipment, which is typically suffers from under monitoring and under maintenance. The second reason ties into scalability. Again, it's much faster to deploy compared with other methods. So it doesn't require manual modeling. It doesn't require, in most cases, again, subject matter experts to build the models and to maintain them. And this is the third point, that during production, speaking of AutoML-based techniques, the models themselves are continuously adapted and maintained by the software, not by humans. So Presenso and today Enlight AI, Presenso, as I mentioned, was acquired by SKF to become part of the Enlight suite. Enlight AI is a data-driven and AutoML-based solution. This is our expertise when it comes to AI, to the AI solution that we have. And after answering the why, or what is the motivation behind AutoML, let's go a bit more technical and understand how it works. So as a data-driven solution, we start by streaming the data from the customer plants, usually the customer historians or existing databases, to the cloud. And here we're talking about the entire set of process data or process tags of all sorts and types: the temperatures, the pressures, the voltages, the currents, the vibration, the fluid levels, any tag, any sensor that is part of the process control. So the first phase is the data acquisition part, in which the customer streams the data to our cloud. Now, looking into the sensors, first of all, there could be thousands of sensors, right? And second, they're very different when it comes to the data characteristics. So measuring high resolution vibration or high resolution vibration measurement is very different than low frequency temperature measurement or any other sensor. And that understanding that we have thousands of different sensors per customers, even tens of thousands, each one of them in many cases with different data characteristics. When we started the development about 5.5 years ago, we came to the understanding that we will probably won't be able to find or develop a single modeling algorithm that can fit all these thousands of different cases. And for that reason, what we've done is that we built a toolbox. A toolbox which contains dozens of different modeling algorithms. Each one with its strength and weaknesses to it. So we have this toolbox with a set of modeling algorithms. Now on top of it, the second part of the work after assembling or starting to collect these tools or develop these tools, the second part is to decide which one to deploy on each sensor. So there's a full automated mechanism in the software that decides, that evaluates and decides which modeling algorithm is the best one to use on each and every individual sensor in the system or in the customer machines. So this is the first part, the auto selection of the modeling tools. And as I've mentioned, machines eventually, either they grow old or they go through maintenance or overhauling. The process changes. So it's always important to validate these selections. In many cases, they could have been made half a year or a year ago. So we need to make sure that the level of performance of the models is kept. For that, after the selection and the auto deployment part that we've covered, there is the auto validation part, which is a continuous closed loop validation of the model. We need to make sure, or the software needs to make sure, that the models correctly reflect the data. And if at any point of time the software detects a degradation in the model, it can go back to the toolbox and either recalibrate the model, or in some cases, as you've seen in the animation, completely replace the model with a new one that now found to be better performing on this sensor. So from the customer perspective, Enlight AI starts with detecting abnormal sensor readings, right? What's known as time series anomaly detection, in that case univariate. So on each and every individual sensor separately. Then of course, customers, and I didn't mention it at the beginning, but I was a support and maintenance engineer myself. It's very important to have and to provide to the user, to the customers, the holistic view of the entire machine. So analyzing each and every sensor individually, it's just a starting point. What is even more important is to then find and extract the patterns across multiple sensors, to identify a specific failure mode or failure pattern and use these insights as an indication to upcoming failures. So we start, or Enlight AI starts with anomaly detection on the sensor level, correlation detection across all the sensors in the machine, and eventually the failure prediction alerts, which are based on features extracted from the data. I would say a bit of data science language, feature extraction. Basically, it means extracting indicative metrics from the data, whether from the raw data, from the anomalies detected, from the patterns detected, etc. How does it all look like to the user? What will you see? So, of course, putting all these insights into an intuitive and user-friendly user interface is important to make these insights actionable. For that, we have several types of visualizations, starting from the global overview that can show multiple sites, then starting to dive deeper into the specific plant or factory view, where you can see the distributions of all machines monitored, statistics over the downtime and MTBFs. And of course, for the technical teams, engineers, technicians, it's important to understand what's going on within each machine, right? So in that case, you can see an example of an anomaly map. So all the sensors in the machine, starting with a light blue area which reflects normal behavior, and then anomalies are detected in a group of 5 or 6 sensors here, which eventually leads to the red area, which is the downtime. And in that case, a prediction alert is sent here once the pattern is detected, while the downtime is only a few days later. Again, as an engineer myself, I really like to know the details of what's going on, and for that we have another view, which is the sensor or tag view, trends view, where we can see the specific anomalies detected in each sensor, whether spikes or drifts or changes in frequency, temporal outliers, contextual outliers in data science language, and also the group of correlated sensors, which they all exhibit abnormal readings in a time period. And here what we can see is that perhaps this black sensor on the bottom here has the first anomalies. This could be the origin of this chain of events which leads to the downtime. So alerting, assisting in detecting the root cause, of course, and aggregating the insights. At this point, usually we present a demo or a live demo of the system of the Enlight AI in action using real cases. Unfortunately, due to the time constraints and the nature of this discussion, I will not present the demo yet. As mentioned, if you have interest, feel free to reach out to the local SKF representative and to ask for a demo. Try to summarize automated machine learning and Enlight AI. A good testimonial would be the fact that Siemens Energy, even though they have their hardware-based solutions of sensors and instrumentation, they have their digital twins, which are physical-based models. They have data scientists, which are manually modeling. Still going through a selection process, Siemens Energy has selected, back then it was Presenso, today Enlight AI, to be their partner when it comes to AutoML and scalable analytics. So strong partnership with them, and of course others. So this wraps up the deep dive into the automated machine learning part. Right? I think we're in a better position now to understand why is AutoML preferred when it comes to scalability. Basically eliminating or minimizing, I wouldn't say eliminating, but minimizing the dependencies on human, and of course the cost, given the cloud, as I said, cost of CPU and data storage today are declining as we speak. But the question is, why choose when you can have it all, right? And in that sense, in some cases, hardware-based solution would perform better. In other cases, AutoML would perform better, or digital twin. And the question, as I said, is why choose when you can have them all? And one of the main drivers for SKF to acquire Presenso and for Presenso to get acquired by SKF is the strong synergy in combining all of these types of solutions together. And today as SKF, we provide all of these solutions, and therefore an end-to-end, I would even say tailor-made solution for each customer depends on the needs they have. So if we're talking about legacy equipment, old plants which are under-instrumented, we have the series of IMXs, which are online vibration monitoring systems. When it comes to experts analysis, we have our rotation equipment performance centers. So regional centers across the globe where data is flowing in from the field in real time, mostly vibration data, to be analyzed by experts. So experts analysis. There are different solutions, again, evolving or around vibration data analysis, which use advanced machine learning solutions or machine learning techniques. In that case, they qualify as the manual data-driven modeling. And now, after the Presenso integration, of course, the automated machine learning, which gives the angle of the process data, not only vibration, but moreover the process data. So basically, an end-to-end solution that could be really customized as per the customer needs. And another strong synergy is in what we call the hybrid solution. Basically taking these two machine learning based solutions with manual modeling, with expert knowledge and the history of 115 years roughly of monitoring and analyzing vibration data and incorporating it into the automated machine learning. So transferring a lot of knowledge from subject matter experts to the algorithms to provide a hybrid solution, and the term hybrid is used because it's a data-driven approach and expert knowledge-driven approach, combining them together into one single solution. And keep in mind that we are SKF, right? So when it comes to remote monitoring and data analytics, this is the suite that we're today offering to the market. Yet as SKF, of course, our main core, I would say, core goods or core products is, of course, the bearing. For various different types of bearing for various different types of applications. Lubrication management, automatic lubrication management systems, and Recond Oil, which is another acquisition that we've made recently for oil rejuvenation, cleaning used oils and recycling it. Application engineering and re-engineering, making sure that our customers use the right bearing in the right application. Remanufacturing. So a bearing can be remanufactured and refurbished up to 3 times, preventing from manufacturing of new parts all the time. And of course, the connected supply chain 4.0. So if the monitoring part predicts a failure in a unique bearing that would happen in 3 months or 6 months into the future, closing the loop with the supply chain to be able to provide, to have a spare bearing on site before the bearing fail in the field is crucial. And it's another aspect of digitalization, of course. Eventually, our vision or driver, I would say, is the environment, of course. Reduce, reuse, recycle, circular economy to reduce the carbon footprint. As it all comes together. So, as mentioned, we have SKF's IMX, which is an online vibration monitoring system. We have the process data from the customer on the other side. We start by streaming all of them to Enlight AI, and in some cases Observer, which is the SKF systems for vibration data monitoring. Data is being analyzed in real time. And when a suspected pattern or a failure is predicted, Enlight AI is generating an alert that is simultaneously sent both to the rotating equipment performance centers and to the customer. The people sitting and working in these remote diagnostic centers, they initiate an investigation to identify the root cause of course, and the effort is to provide the customers with a corrective action recommendation. Corrective action recommendation could be tied specifically to the bearing in the field and could be also tied to lubrication, lack of lubrication. If it's a repetitive failure in the same bearing, perhaps re-engineering and finding a better bearing for that specific application is the corrective action. Of course, remanufacturing if needed, and supply chain. So all of these are in the back pocket of the people in the RDCs or in the remote diagnostic centers in order to provide the best mitigation or corrective action recommendation back to the customer. And this slide summarizes all the cycle, I would say, from the technical or service perspective. And as you might recall at the beginning of the presentation, we were discussing also the disruption that this new technology induces or causes when it comes to the business models. And looking at the business models, as discussed, the total cost of ownership is pretty much comprised from these 3 segments, while looking at this traditional business model, the OEMs would always want to sell more, right? Sell more equipment, sell more bearings, or sell more machines or spare parts, while the end user's incentive is to buy less. And this results in an inherent conflict here. And in order to align the interest and to overcome that inherent conflict, what we believe today is in performance as a service. This is the way going forward to align the interests of the OEM or the equipment or the component manufacturer and the end user. So in SKF today, when we look at this model, we offer today rotation for life type of contracts, which is a service contract, where we work together with our customers to reduce the downtime to minimal possible, to generate savings, which we then share together with the customer in a fixed fee and performance-based business model. And this is how we align the interests of our customers and ourselves. To summarize, eventually, our focus is on cost-effective and reliable rotation. And looking at this new Industry 4 era, we have all the enablers to do so. Starting with the digitalization, whether of the data analytics part, whether the supply chain, connected supply chain. We have this new business models from transactional to fee-based plus bonuses, performance part. And eventually, I think a common driver that should be important to all of the players in the world is striving for a green, circular economy and reduction of our carbon footprint. Good. So this is the introduction presentation. As mentioned, there is a lot to it, and if you wish to learn more, feel free to contact us. I would be happy to answer questions now, and let's see, what do we have? Okay. Are these models of predictive MT available? I'm not sure I completely understand the question, predictive MT, but all these models that I've presented in this slide, or even better to look at this slide, all these models are available. I mean, this toolbox is there, fully operational. The models are being trained and built per specific use case. Okay, there is also the option to transfer the models, what we call transferred learning, from one machine to a similar or identical machine to shorten the training process. So the question was, are these models of predictive MT available? Yes, they're all available. Is that possible to have a presentation via email? So this video or this webinar is recorded, and soon it's going to be published on our YouTube, SKF YouTube page, and you can review it as much as needed. And as mentioned, always you can contact SKF people. Next question. What is the mean time spent required for AI computing to develop, model, and predict? This is a good question. It should be addressed in two aspects. One is the time span and also the data, the availability of data. So normally the time span would, again, when it comes to AutoML, it will be a couple of weeks, or let's say 4 weeks, 2 to 4 weeks to have the models fully trained. And this is under the assumption that the data is there, meaning we have historical data to train on. Roughly speaking, again, depends on the use cases, but somewhere between 12 months to 24 months, I would say. If the more, the better. So we train on historical process data. We train on historical failures. And then the configuration time or the deployment time of the solution is within the, let's say, 3-4 weeks. The next question is here, why AI doesn't predict root cause as still it is getting data from particular sensors? Good. AI is able to detect root cause, yeah, as we've seen in this example here. Clearly, in that case, this pattern is regarded as the root cause, yet at this point, the software will provide an indication of which are the most abnormal sensors and which are the correlative patterns detected for which the alert was sent. In the future, and this is currently under development, again, also using or incorporating expert knowledge from SKF side, is to present the exact root cause identified based on historical events detected or trained on in the past, and based on some level of expert knowledge injected into the system. So AI currently identifies the more suspicious behaviors that can be regarded as a potential root cause. Next question is, so basically in the form of sensing. Yeah, so next question is, so basically hardware in the form of sensors is required for all methods. Just computing and analyzing methods change, is it? Eventually sensors, they are the source for data, so they are required. If they're not there, these three methods or software methods will probably not work. And in that case, where sensors are not available, the first step would be starting to instrument these processes or machines, most likely with new vibration sensors. So these hardware solution of the IMX is quick to install and already provides indication of failures as these IMXs are connected to the RDCs. So in that case, there will be a direct line here without going through Enlight AI. How good we can be able to recondition of hydraulic oil? Okay, there is a question here on the reconned oil. So I'm not the expert here. I'm hearing that it's a revolutionary solution to reuse, to clean and reuse oil, hydraulic oil from nanometers particles. Here too, question comes from India, Wheels India Limited. I would suggest you contact your local SKF representative and they will be able to gather more information on the reconned oil solution. Gerard is asking, do you have examples of equipment or factories which managed to reduce their spend by using similar tools? What is at stake? So yes, we have examples from mostly from the energy, oil and gas, steel manufacturers, mining, which are using our solution and predicting failures somewhere between, in the lowest end, I would say 5-8 hours up to 3-4 weeks before an actual failure. What's at stake? What the customers are needed to do are to invest in the process of onboarding. Usually it's a 4 weeks proof of concept project where we analyze historical data and show the results. Perhaps I have a slide here that exemplifies the results. So this is an example of several processes that we've, selection processes that we've went through. Against competition, as you can see, always against competition with feed pumps in power plants, continuous clusters in steel plants, gas turbines with an OEM, and turbo compressors in oil and gas. You can see that the Prediction performance score ranges from 80 to up to 94. This also relates to the amount of data that we have. So one machine, 45 sensors, compared with 10 machines, 500 sensors, and also the number of events in the data. And predictions can range from 20 days maximum in this case to an average of 5 days in other cases before the failures. Thank you, Joab. So these are the examples also to your next questions. Which process data contains the most valuable information apart from vibration sensors? So this is really process dependent and machine dependent. I can tell you that it really varies from one use case to another. We're talking about temperatures, motor currents, pressures, everything that is in the process data, but it's a good point because we don't want to take garbage sensors, let's call them. So we do conduct a workshop with the customer, which actually it's a couple of hours, to understand or which sensors we should focus on. We do not want to fool the entire analytics stack with sensors which are meaningless. And there are also statistical measures to reduce the number of sensors and to extract, understand which are the more indicative one. You can read about PCA and feature extraction. The next question is, we have 8 more minutes. What is the range of data in terms of number of data points for predictive maintenance to be possible? Okay, good question. So in order to, I would start like that. First of all, it's always dependent on the physical processes, right? We want to make sure that enough data is represented or enough physical phenomena are represented in the data. So the high level answer would be, it really depends again on the process and use case. From the data science perspective, to start working and generate the initial sensor models, we would need roughly 20,000 samples. What are the data points required for predictive maintenance? What parameters? So as I've said, really depend on the process. We work to understand, or we ask the customers to provide the sensors which they consider to be more representative. Usually we're talking about dozens of sensors per machine or component. So minimum would be 20 and up to 100, 150 sensors per component. How accurate is the root cause failure analysis provided by the system? Is human interference required? So yes, when it comes to root cause failure analysis provided by the systems, currently the Enlight AI provides the list of, or the representation of sensors which were found to be the most abnormal. Still, we learned that it's more of a suggestion than a suggestion for the customer to start investigating than identifying the root cause. And in that sense, where there is work in the back or the development side to incorporate some expert knowledge, whether from the customer, some failure modes example that they're more important, or from SKF, which, you know, there's a lot of expertise around failure modes in bearings, to be able to make a more deterministic identification of the root cause. This will be released in the upcoming month. What other parameters other than temperature, pressure, and vibration can AI measure? So AI doesn't measure any parameter. AI analyzes the data and again takes everything in the historian, whatever the customer can provide. Okay, the value at stake, I meant the value at stake for specific equipment like verticals, mill, and cement plants. So of course the value, you know what, let me give you a nice example from cement. Working with one of the largest cement manufacturers, the value at stake for them if they don't use predictive maintenance in general and predictive analytics in more particular is downtime, and painful downtime. In many cases, such downtime that can put the entire line out of production for hours and even days. One interesting use case from the cement industry is the formation of residue rings within the rotary kilns. So basically chunks or lumps of roughly stone-like materials that is being accumulated on a rotary kiln. And these lumps, chunks of material are then become so heavy that they detach from the kiln and are fed into a crusher down the line, which is not able to cope with them and basically either breaks the crusher or stops it if it's not that big. And working closely with the cement manufacturer, we were able to build a predictive model using sensors coming from the rotary kiln to predict the formation of these residue rings and to alert in advance before they detach and fed into the crusher and stop their production. We're talking about hundreds of thousands of euros or dollars per kiln per year, multiplied by the number of kilns that they have, which is in the hundreds. We're talking about tens of millions, if not more than that, just from that specific failure mode that we're now able to predict. Good. So last question, and then I think, 2 last minutes. Do you have experience on applying AI on machine tools? As you know, the machine tools process may vary either speed, loading, and tool status, etc. Yes, so this is a good question. Most of the examples that you've seen here today are from the process industry and not from machine tools or discrete manufacturing, exactly because of these points that you mentioned, Steve, is that when you look at the process industry, in many cases, the production is much more stable. So it's a lot easier for the algorithm to model the production, to converge, and to predict. When it comes to discrete manufacturing and machine tools and more specific, in many aspects, the production is very random, right? Batch production and different setups and configurations of the machine. So it's much more difficult, I would even say impossible, to predict the behavior of the machine, especially when we want to keep the ability to scale quick. So we do not want to depend on human knowledge too much. So for that specific question, these solution Enlight AI, which I've presented today, is designed more for the process industry rather than the discrete manufacturers. Good, so we were actually able to cover all questions. Thank you all for the interest and for joining us today. Hope it was meaningful for you. And as I've mentioned, feel free to reach out to SKF people if you have any further questions. We'll wish you happy and safe times given this Corona days, and looking forward to continue the discussion with the people who find it more relevant to you. Thank you all. Till next time.